Alright class, so this is the second video for our week 11 lecture. So I hope before you go through this video, you had finished watching the first video. So again, let me just repeat. So when we learn about input-output chapter, okay, chapter 4 is about input-output. So we are actually trying to understand on how to write the coding and also how to connect input-output components to this board. So again, this is an mbed board. So we call this as mbed board. So mbed board has a microcontroller LPC1768 over here, okay, in which this microcontroller, the core of the processor inside is ARM Cortex-M3. Okay, so how do we know that? How do we know that the LPC1768 has ARM Cortex-M3 core inside? Okay, so this is where we can refer to the user manual. So inside this user manual, if you refer in your user manual, alright, in our UTeM, I already uploaded the user manual. So you can see on page 12, the block diagram of LPC1768 block. So inside we have all this block, and in one of the block over there, we can see it has this ARM Cortex-M3 core inside. Okay, so this is how we know that this LPC1768 is actually has the ARM Cortex-M3 as its processor core. Other than that, based on this block diagram, we also know that inside this LPC1768 chip, it also has all these other peripherals inside, and one of those is ADC. Okay, 12-bit ADC over here. So this one stands for 12-bit analog to digital conversion module. Okay, so this is one of the modules of many other modules available on the LPC1768 microcontroller chip. Focusing on this ADC module, so the function of ADC module in the microcontroller chip is to convert an analog voltage level to a digital number. Okay, so why is that? Because microcontrollers can only process digital numbers but not analog numbers. And how to do that? So this is where we can refer to the previous video, that is through the three processes. The first one is through sampling, and then quantization, and the next one is encoding of the analog value into its digital form. So if we look to the next slide, okay, so this is, for example, okay, so the value read from the analog sensor, okay, in which when it go inside the analog to digital conversion module in the microcontroller, so what happens is that the modules will convert the value into its digital form. And so here, 87 is just an example, a number in decimal for the digital value that had been converted by the ADC module. Okay, so if we zoom in inside this block over here, alright, so recall that, for example, if let's say we have many quantization levels inside, alright, in which the step size for each of the levels in this case is 0.1 volt, for example. Okay, so if for the value for 2.343 volt obtained or captured from the analog sensor outside the system, okay, so it falls within this range of voltage, which is between 2.3 to 2.4. So here, okay, so the value that will be understood by the ADC module inside the microcontroller is 87. So this 87 is in decimal. Okay, but then when the microcontroller read the value, so this value actually will be converted into its hexadecimal form. So this is the specific figure, okay, or the specific block diagram for an ADC module inside the LPC1768 microcontroller. Okay, so the ADC module using successive approximation register to convert its analog input into its digital form. Okay, so this is from this figure, what we can get is Vin is actually the value read from the analog sensor, which will go into the SH block over here. So this is actually sample and hold circuit, okay, in which this value will be compared, okay, with the voltage reference of the system. So this one actually usually is fixed by the system or the circuit designer, okay, by us ourselves. But then if let's say we use our LPC1768, so the voltage reference for this circuit is 3.3 volt. And this clock is actually the clock of our microcontroller. Alright? So this is how it looks like inside the ADC module for the LPC1768 microcontroller. If we want to read the digital value after it is converted by using this ADC module, so we have to read this successive approximation register value inside. So we have to read what is the value stored inside this register. Then only we can get the converted value. Okay, so for ADC module, usually it has this term called as resolution. Okay, so this resolution stands for the number of bits that is used by the analog to digital conversion module to represent the digital value. Okay, so these are just an example of n bits for an ADC module. So sometimes in the module it uses 8 bit, 10 bits, 12, 16 or 24 bits for its resolution. So as we can see, the higher the resolution, the better the accuracy of the converted value. Okay, so why is that? Because higher number of bits will give a higher number of steps. So in which higher number of steps will give a more smaller step size, okay, in which when it is being converted, the value will be much more closer to the real sample value. Okay, so this is why the higher the resolution, the better the accuracy of the analog to digital conversion module. This is the formula that can be used to get the converted value. So as we can see over here, so Vin stands for the input voltage captured by the analog sensor. Okay, divide by step size is the step size of our ADC module. So let's take a look at one example. If in our ADC module, the number of bits or n is equals to 12 bits, so this is the ADC resolution, 12 bits. So the steps for the ADC module is equals to 2 to the power of 12, which is equals to 4096 steps. And let's say the reference maximum voltage for the ADC module is 3.3 volt. So this is the information that we have. So if we want to know what is the converted value after its conversion, okay, if the input voltage or the voltage read from the analog pin is equals to 2 volt. So if we use this formula, so the digital output value is equals to Vin over the step size. So first we have to know what is the step size of our ADC module. So the formula for the step size is the maximum reference voltage divided by the number of steps. So in this case, the maximum reference voltage is equals to 3.3 volt divided by the number of steps is equals to 4096. So based on this value, so we plug in inside our formula. Okay, so the output digital value is equals to 2 divided by the step size, which is equals to 2482 in decimal. Okay, so this is the converted value that we can get from the ADC module based on this formula. Alright, but then if let's say we read the value inside the register, inside the microcontroller, okay, so what we will read is, we will read the hexadecimal value or its binary value. Okay, so usually we will get this one, 9B2 as the value from the register. Okay, but then based on the calculation, we will get its decimal value. So this one we have to know how to interchange between the decimal value and the hexadecimal value. In this slide, we are given the illustration showing the upper reference voltage value range and the lower reference values range of an ADC module. So as you can see over here, the upper reference voltage value can take the range between 2.5 volt to 5 plus 0.3 volt. Okay, and about the lower reference voltage, it can take the values that fall within these blue colored lines over here. Okay, so why is these values important? Okay, so because this value can be used to calculate the step size of our ADC module. So how to do that? So based on the positive or based on the upper reference voltage, for example, in this case 5 volt, and if let's say the ADC module, the lower reference voltage is 0 volt, okay, so in order to calculate the step size, okay, so we need to use the formula 5 minus 0 over, okay, over the number of steps available in the ADC module. So how do we get 256 values over here? So in this example, the resolution of the ADC module is 8 bit. So when it is 8 bits, so the number of available steps is equals to 2 to the power of 8, which is equals to 256 steps. So that's why we have these 256 values over here. So for each of these ADC modules over here, okay, for the respective upper reference voltage and lower reference voltage. So this is the step size for each of this system. Okay, so I hope this table is clear for you. Okay, so in this case is equals to the number of equals to the value of the input voltage from the analog sensor that the system can handle. Okay, so from 0 to 5 for this when the upper reference voltage is 5 volt. For a system where the upper reference voltage is 1 volt, then the input voltage that can be captured from the analog sensor is from 0 to 1. Okay, so this is what it meant from this slide lah. Alright. Okay, I hope based on what we had covered so far, so you can try out this example. Try to calculate the digital output value if the analog input is 1.7 volt and 2.1 volt. So assume that the ADC module has the resolution of 10 bits and the maximum reference voltage is equals to 5 volt. Okay, for the lower reference voltage, so assume that the value is 0 if it is not given in the question.